They appear without warning, expanding to the height of a multi-story building, and annihilate everything in their path, claiming thousands of lives. No, these aren't monsters from blockbuster movies. I'm talking about regular seawater forming a tsunami. If you think this won't affect you, think again. How can you detect such a looming threat, and how does the ocean generate such devastating waves? Hello, and welcome to ZE. Please don't forget to subscribe and hit the bell icon. The greatest danger of a tsunami lies in its suddenness. In Japanese, tsunami translates to harbor wave, a term coined by fishermen who return to find their port obliterated by an unseen massive wave. In the open ocean, tsunamis are generally no taller than a meter or 3.3 feet. But the distance between the wave crests can range from 100 to 200 kilometers, 60 to 120 miles, making them 1,000 times larger than typical waves. Their speed is comparable to that of a jet plane, and they only grow to monumental sizes when they reach the coast. So, how do we account for this sudden ferocity? Unlike ordinary waves, which are wind-driven, the immense water mass of a tsunami is propelled by a short, powerful underwater impulse, causing a significant, abrupt shift in the ocean. This may result from an earthquake, volcanic eruption, landslide, explosion, rock and glacier collapse, or an asteroid impact. However, the primary cause, in 88% of cases, is seismic activity. The energy driving a tsunami travels through the water, not on its surface. Consequently, 95% of a tsunami's life cycle is invisible, only surfacing at the very end. Now, let's delve into the epicenter of these events, where the lithospheric plates of the Earth's crust shift. This powerful shake, almost 8 points on the scale, means a tsunami is inevitable. The shock causes part of the seafloor to rise while another part sinks, making the ocean oscillate vertically and triggering waves. If a ship is positioned above the earthquake center, it remains safe as the waves hitting its side are only about half a meter or 1.64 feet high. But in the ocean depths, everything trembles from bottom to surface. Imagine this colossal water mass rushing towards the coast at speeds of 400 to 880 kilometers per hour, 249 to 547 miles per hour, and sometimes up to 1,000 kilometers per hour, 621 miles per hour. What would you see from the shore? If you're expecting a monstrous wave like in disaster movies, you might be unprepared for the reality, which could cost you your life as you stand mesmerized by the unusual water behavior. Before a tsunami, the water often recedes, exposing the seabed due to land subsidence at the earthquake site. The worst thing you can do at this moment is to collect shells and marine life from the seabed, as many first-time tsunami witnesses have done. Meanwhile, part of the wave near the coast slows down to 50 kilometers or 31 miles per hour, and the remaining water mass begins to rise due to congestion. The deeper the ocean, the higher the crest, and the more the water recedes, the larger the tsunami. Now that you understand this strange behavior, you can warn others of the impending disaster, just like Tilly Smith did on the Indian Ocean coast in 2004. She had learned in geography class that the water recedes quickly before a tsunami and convinced her parents and those around her to flee, saving about 100 people. Remember, you must act swiftly, despite slowing down. Once the wave hits the shore, its speed remains in the tens of kilometers or miles per hour. You have a maximum of 20 minutes once an alarm sounds or a tsunami appears on the horizon. Use this time to move 10 kilometers or 6.2 miles inland. If that's not feasible, climb onto a roof or a sturdy tree. A car might not be the best option due to potential traffic jams. If you're caught in the water, remove heavy shoes and clothes immediately. Debris can hit you and drag you into the ocean, making it difficult to escape if you're weighed down by clothing. Also, don't rush back to the danger zone once the water recedes. This mistake cost the residents of Severokurilsk in 1952 dearly. After surviving the first wave, many were swept away by a second wave, which was 15 to 18 meters, 49 to 59 feet high, half an hour later. Multiple waves are common, and the first isn't always the largest. Subsequent waves might not arrive for 2 to 3 hours and will face no obstacles. The first wave clears the path, taking cars, trees, and property, while the second wave brings it all back, demolishing buildings and anything in its way. This is exactly what happened in Severokurilsk. The tremors started at around 4 a.m., and by the time the morning fog cleared, the only remnants of the city were fragments floating in the water. It is essential to wait 3 to 4 hours after the final wave before breathing a sigh of relief. But don't rely solely on the water's strange behavior for salvation. Tsunamis don't always cause the water to recede first. The most reliable information comes from tsunami warning centers, as seismic waves travel much faster than water waves, providing coastal residents with crucial minutes or even hours of warning if the earthquake's epicenter is far enough away. Not all strong underwater quakes result in tsunamis. Monitoring an increase in water level in specific sea or ocean areas offers the most accurate forecast, and it's vital that the alarm from the measuring point arrives no later than the wave itself. While discussing underwater earthquakes, other tsunami causes shouldn't be overlooked. For instance, the largest tsunami ever recorded occurred in Alaska, where 90 million tons of rock and ice fell into the bay, propelling water 524 meters, 1,720 feet, into the air. A wave swept across the bay, uprooting trees and hurling a ship 10 kilometers, 6.2 miles, from the epicenter across an island. The tsunami caused by the Krakatoa volcano eruption in Indonesia in the 19th century destroyed thousands of ships and claimed tens of thousands of lives, even though volcanoes account for only about 5% of such disasters. Tsunamis can also be triggered by human actions, such as underwater atomic bomb explosions. In the mid-20th century, one such explosion lifted a wave 29 meters, 95 feet, high, though it caused no damage as it calmed down after breaking 300 meters, 984 feet. The rarest tsunami causes are asteroids over 1 kilometer, 0.62 miles, in diameter hitting the water. The Chicxulub asteroid, with a diameter of 11 to 81 kilometers, 6.8 to 50.3 miles, and a crater 20 kilometers, 12 miles deep, is believed to have caused the extinction of dinosaurs. It blocked sunlight by releasing dust into the atmosphere and triggered a tsunami 14 meters to 1.5 kilometers, 46 feet to 0.93 miles high, stirring the planet's oceans. The deadliest tsunami recorded occurred near Sumatra in 2004, affecting 14 countries and claiming over 200,000 lives. The earthquake that triggered it released energy equivalent to 20,000 Hiroshima atomic bombs. If you're hesitant about your future vacation plans, consider that the greatest tsunami risk lies in the Pacific Ocean's Ring of Fire. Even there, significant waves occur no more than 4 times a year and only once a decade reach heights of 10 meters, about 30 feet. Tsunamis are some of the most formidable natural disasters known to mankind. These giant waves, often originating from underwater seismic activities, have the potential to devastate coastal regions with immense force and unpredictability. Understanding how giant tsunamis work involves delving into the complex interplay of geological processes, ocean dynamics, and the forces of nature that give rise to these monstrous waves. The genesis of a tsunami. The majority of tsunamis are triggered by sudden displacements of the ocean floor, primarily due to underwater earthquakes. When tectonic plates shift, they can cause a significant vertical movement of the seafloor. This movement displaces a massive volume of water above it, generating waves that propagate across the ocean. The energy from these disturbances travels at tremendous speeds, often reaching up to 500 miles per hour in deep water, akin to the speed of a commercial jet plane. In addition to seismic activity, other phenomena such as volcanic eruptions, landslides, and even meteorite impacts can also generate tsunamis. However, underwater earthquakes remain the predominant cause. The severity of a tsunami is often proportional to the magnitude of the seismic event. For instance, a magnitude 9.0 earthquake can displace the ocean floor by several meters, producing waves that can travel vast distances with little loss of energy. The journey across the ocean. Once generated, tsunamis travel across the ocean as a series of waves known as wave trains. Unlike regular ocean waves, tsunamis have long wavelengths, often exceeding 100 kilometers. This characteristic allows them to travel across deep ocean waters with minimal energy loss. The waves may be imperceptible on the ocean's surface, making them difficult to detect by ships or satellites. It is only as they approach shallower coastal waters that their true power becomes evident. As a tsunami approaches the continental shelf, the decrease in water depth causes the waves to slow down but increase in height, a phenomenon known as wave shoaling. The energy that was dispersed across the vast ocean becomes concentrated in a smaller volume of water, leading to a dramatic rise in wave height. This transition from deep water to shallow water dramatically amplifies the tsunami's impact, turning it from a series of undetectable ripples into towering walls of water that can reach heights of over 100 feet. The impact on coastal regions. The impact of a tsunami on coastal regions can be catastrophic. Upon reaching the shore, the tsunami's energy is unleashed with devastating force. The waves rush inland, carrying debris, sediments, and anything in their path. This surge can flood large areas, destroy infrastructure, and cause significant loss of life. The destructive power of a tsunami is not limited to the initial wave. Subsequent waves, known as wave trains, can continue to hit the shore for hours, further compounding the devastation. The effects of a tsunami are also influenced by the coastal geography. Bays, estuaries, and other natural features can amplify the wave height, creating localized areas of extreme danger. Additionally, the speed and force of the waves can lead to strong currents and backwash, which can trap and drag individuals, vehicles, and structures back into the ocean. Mitigating the risks. Understanding the mechanics of tsunamis is crucial for developing effective warning systems and disaster preparedness strategies. Seismologists and oceanographers use a combination of seismic sensors, tide gauges, and deep ocean assessment and reporting of tsunamis (DART) systems to detect and monitor tsunamis in real time. These systems can provide critical data that help predict the arrival time and potential impact of tsunamis, allowing authorities to issue timely warnings and evacuate vulnerable coastal areas. Public education and community preparedness also play vital roles in mitigating the risks associated with tsunamis. Awareness programs and evacuation drills can significantly enhance a community's resilience to these natural disasters. Moreover, coastal infrastructure can be designed to withstand tsunami impacts, incorporating features such as seawalls, tsunami-resistant buildings, and elevated roadways to protect lives and property. Have you ever experienced a tsunami or another natural disaster? Share your story in the comments. If you enjoyed this video, give it a thumbs up, subscribe to the channel, click the bell for notifications, and recommend us to your friends.